Cool. All right, yeah, so I think the integrity theorems are some of the most interesting theorems that we have, because these are the ones that tell us how to build systems. All right, so if we rewind a couple of years, I did episode 1 of this talk at the seL4 Summit hosted by the Trusted Computing Center of Excellence. And in that talk, I wanted to give people who build systems a little bit of an insight into the proofs and what they mean, what their significance is, and what the symbols actually look like in the theorem prover. And that was a lot of fun. Maybe type 2 fun, but still fun. So that talk, was focused on the abstract spec and the invariants. And so that's sort of the description of what seL4 is and some proofs about its internal consistency. And that's just like the core of the proofs, and the details are interesting. This year, I want to talk about the integrity proofs, which is the first of the 2 security proofs. This talk will be a bit different because now the details are less interesting, but the concepts are a bit more weighty. So there are two lots of security proofs. Integrity talks about access control for write operations, and confidentiality is about read operations. It's a little bit crude, but it's good enough. Right, just full disclosure, integrity proofs were proved in 2011, published in this paper, not by me. There's a bunch of authors there. Two of them are here with us today. That's, of course, June and Gerwin. So why do I want to talk about it today? They're quite interesting to me right now because I've joined Crichton. We're building an operating system on top of seL4. And of course, we want first-class security and reliability, and isolation is a really strong part of that. And of course, we want to get that from the integrity proofs. But we also want really strong manageability. And for that, we need a very dynamic system. Like, for example, we already have a web-based command and control console where an operator can reconfigure a remote system, install apps, upgrade apps, uninstall apps, resize apps, all without rebooting the system. So we need a lot of dynamic features. Do the integrity theorems even work there? So that's what I sort of want to know right now. Before I can tell you what's going to happen in this talk, we need to cover some basic concepts. There are sort of 3 key questions that these proofs ask us. The first one is, if we have a system that's a series of states, a series of state transitions, do we want to allow this state change to happen? So we've got 2 states here. There's a lot going on inside each state. They're going to be different. There's going to be state change there. Is that state change okay? So how do we answer that question? Well, if you're an seL4, someone experienced with seL4, you'll think about that in terms of capabilities. We can look at an individual state to determine sort of the inherent authorities in that state. So if we have, you'll see this word subject a lot. So that is the agent that is currently taking an action. So we'll label TCB there with T, and that's the current subject that's initiating this transition. We want to know if the authorities that that agent has are sufficient to describe the changes that have happened. So we have a TCB here with a C node, a page table, and a frame. So we'd expect that that thread is allowed to change this frame that it's set up to access. There's another frame here that's sitting out on its own, and we would expect that a change in that frame would not be allowed by that subject taking a transition. So that's sort of the basic question that integrity asks. But of course, the detailed capability model is it's too detailed for the kind of reasoning we want to do here. So instead, we make a more abstract policy language for talking about system design, and these allow us to hide the detail in a component. Now, if we have a policy that describes how we want a system to behave, We somehow need to relate it to the state of the system. Like if there's some authority in the state that's not represented in the policy, then we can't expect that transition to respect the policy. So we have this idea of policy refinement, which is a relation between a policy and a state. We want to know that all of the authorities that are inherent in the state are somehow represented in that policy. Now, of course, it doesn't stop there because this system is going to make another transition. We want to do ask the same question about this transition, so we need a policy to describe this state. And so the third question we ask is, can we just use the same policy? So that's authority confinement, which tells us that if there is a state that is in relationship with a policy and we make a transition, then we can use the same policy for the next transition. It's called confinement because if the system is constrained to behave according to the policy and we use the same policy, then we know that the authority has not propagated arbitrarily. Okay, so those are the three basic concepts that we'll sort of explain through the talk. But I want to briefly talk about the process of theorem proving. This is very simplified, but there are sort of two basic activities that we do. We state definitions and then we prove some theorems. Stating a definition is just identifying some concept that we think is going to be useful. It's an expression or it's a function, some predicate. We just write it down and give it a name. The hard part about writing definitions is figuring out what are the useful concepts. The second step is that we prove theorems, and these still have names, they still have a bunch of expressions in them, but we have to do a proof. Okay, so why is this an important distinction? Well, let's just look at some definitions first. Remember we had the arrow going across, where we asked about integrity. Is this state transition allowed? So we talk about that with the integrity definition. So integrity is defined as a function of three arguments. It takes a policy and a pair of states. And it just says, if that's the difference between those states respects the policy, then integrity should return true. Otherwise, it should return false. PAS-refine talks about the policy refinement relation. That's this one here, between a policy and a state. But it's just one state here telling us whether the policy captures all of the inherent authority in this state. So it's just another function, two arguments, returns true or false. We have two theorems now. One of them is an integrity theorem, and one of them is the authority confinement theorem. So remember, authority confinement goes across the top, telling us that we can still use the same policy. Integrity tells us that if we have policy refinement, then the state transition respects that policy. So now we have four things, but we only had three on the previous slide. So the reason I wanted to make this distinction is that we have two things called integrity, and I want you to pay attention to which one I'm talking about. One of them is a definition, and one of them is a theorem. So we have to do work to prove that these theorems are true. Okay, so now I can tell you how this talk's going to go. We're going to talk about what do policies look like, and how do we write one down. We're then going to show how we prove that, or how we show that a policy and a state are in that policy refinement relation. Then we'll sort of recap what the theorems tell us if we have those two things. And then finally, we'll talk about how we actually build systems using those theorems. Okay, so let's look at an access control policy. I have a little example system here. It's just a couple of threads, C nodes, page tables, frame, bit of untyped memory, and some notifications endpoints and a shared frame there. So how do we make a policy? Well, first step is just to draw some boxes around things. Typically, we would take the private resources of a thread all together with the thread itself. So we get sort of a box containing a bunch of resources. But the shared things, we typically separate them out into their own components. The reason for that is that it gives us a better picture of the interactions that can happen between the active components. Because drawing boxes around things is the same as labeling the individual things. So if we just individually label all of these as server resources, that's equivalent to drawing a box around them with the label server on them. So in the actual formalization, we represent that as a function from a resource, which is just an address of a thing in the kernel, to the label of that thing. Okay, the second part of defining a policy is then drawing arrows between the boxes telling us what authority they have over each other. Okay, so server component here has receive authority to the server endpoint. The client has sync send on that endpoint. Okay, so in the formalization, we represent that as a set of triples. We just have two labels and an authority. Okay, and these are just the types of authority that we can have in the system. There are a few for talking about communication with endpoints, some for talking about protected procedure calls, read and writing frames, and then everything else is bundled into this control authority. Now, the reason for that is that there are a bunch of things that it's not useful to try to separate. A bunch of things that you can't meaningfully separate into different components. Like if one component has a cap to a TCB, and another component, then you can't meaningfully talk about those as separate components. So we just bundle all those things into a single authority called control. Okay, so we've talked about how to define an access control policy. The next step is to show that that policy is somehow in relation with the state of the system. Okay, so there are actually two parts to this. The first is what I said before, that we would need to show that the protection state sort of has maps onto the authorities in the graph. Now, you might have noticed that the arrows that are going between these components kind of look like the arrows going between the components here. And that's because every authority that's in the detailed model somehow needs to be represented in the more abstract model. And so PAS refined, which is the thing that defines that policy refinement relation, captures all of the ways those authority can be present. Just a couple of examples. If a TCB has a cap to a C node, then the TCB's component must have control over the C node's component. Again, if you have a cap to a TCB, you can't meaningfully separate that into a separate component. Similarly, if you have a C node to some untyped from which an object has been allocated, you also have that control relation. Now, we have some choice about how we draw the boxes. So if I draw a box around the individual bits, then I get two components with a control arrow going between them. But I can also choose to just draw a box around the two components and just assume that those arrows are sort of internal to that component. Arrows inside a component are not really meaningful, so we don't bother to draw them. A couple more examples. If you have a page table and a frame, that's actually, yes. Yeah, then the components must have that right authority. And again, you can just draw the boxes how you want. And a final example, that it's not just about the capabilities. If a TCB is blocked sending on an endpoint, then the TCB's component has sync send authority of the TCB's endpoint. That recognizes that the time of check to time of use issue is here, and that you can become blocked on an endpoint and then lose your capability, but you still have authority at that endpoint. Okay, the second part of policy refinement is that we impose some extra conditions on the policy. And these conditions kind of mean that we can restrict our attention to sensible system designs. And that simplifies the model without reducing its utility. There are two important conditions. One is that grant authority, which is what you get if you have a grant right on an endpoint, implies mutual control. So grant is a very powerful right, and it basically means if you want integrity, you can't have grant between components. The second really important one is that the subject, which is the agent that is currently taking an action, cannot have control over another component. And that's really relevant for the way we build systems and the difference between static systems and dynamic systems. We'll see that later. Now, an important thing to notice is that policies and policy refinement are subjective. Remember, the subject is the agent that is currently taking an action. And because we have this condition that the subject cannot have control over another component, it means that these policy refinement relations are relative to which agent is the current subject. Okay, so we've seen how to define a policy and how to show that it relates to the state. And now let's just review what those theorems tell us. Okay, so the first theorem is the kernel integrity theorem, which says that if you have a state that defines a policy and you take a transition as the subject identified in that policy, then the transition will respect that policy. And that's what integrity says. And the way integrity is phrased is it's just a sort of big list of the ways that the state is allowed to change given the rights in a policy. So for example, if frame contents are allowed to change if the subject has a right access to the frame's component. Yeah, and another example is a thread can be restarted if it's currently blocked and some other component, and the subject has sync send authority to the endpoint. Okay, second theorem, authority confinement, tells us that the policy is preserved. So once we make a transition that's from a state that is in relation to the policy, then we get a new state that's in relation to the policy, and that allows us to continue reasoning about the system. Okay, so those are the two theorems, and that sort of really tells us that seL4 can, implement an access control policy. Okay, once again, the theorems are subjective because, and the most important part of that is that the rights that are important for a transition are the rights held by the subject. Remember in the first example we had a frame that was out on its own, and presumably there's some other thread that has access to that frame, but that's not important because it's the subject that is taking the action. Okay, so we've seen how to set up a policy, how to show it relates to a state, and what we get from the theorems if we have that. Now I want to talk about what that means for building systems. But first we need to sort of think a little bit more about what this subjectivity means. Remember, we've seen that policies identify a subject, that refinement is subjective because we have that well-formadness condition that says that the subject cannot have control over anything else. And the theorems are subjective because it's the rights of the subject that are important for telling us what the transition is allowed to do. But if you think about what that means, is that we have to switch subjects whenever we have to switch policies whenever we want to switch subjects. So we have a series of 3 states where some subject A takes an action and then subject B takes an action. We need a policy that is in relation to the initial state for subject A, but here we need a policy for subject B. So what gives us the right to switch policies there? And it depends what kinds of system you have. In a static system, it's really easy. We constrain. In a static system basically means that all the components are untrusted, so no component has control over any other component. And this means there's no authority to redistribute resources, and also policy well-formadness is no longer subjective. That's because if no component, the only subjective part of the policy refinement relation is that the subject can't have control over anything else. Okay, so that means that policy switches are free. We have a policy here that's well-formed for both A and B, and that's what we need for the next transition as well. So static systems are really easy because you just need some tools that will tell you that the system is well formed for all the components, and then a loader that establishes initial state that is in relation to the policy, and then you know that access control is maintained for the entire execution. Cool. Dynamic systems get quite a bit more interesting. So this is a slightly more complicated system where we have two subsystems that are, in this case, independent, two supervisors which have control over three components which are sort of interconnected by some passive resources. Now we want to get from this state where subsystem 2 has three components to this state where E and F have been replaced by a component G. And this reuses the resources that were previously consumed by E and F. Okay, so remember, to have a well-formed policy, you can't have control over another component. So we can't use this policy to talk about what S1 or S2 do, because S2 has control over D, E, and F, S1 has control over these ones. But this is fine for reasoning about A, B, and C, and D, E, and F. Okay, so we can make an initial transition where any of the untrusted components take a transition. For that, we need a policy that is well formed for these components. But now we want to talk about S2 taking some actions to sort of reconfigure its stuff. We can't use this policy because it's not well formed for S2. What we can do is redraw the boundaries to make a new policy. In this one, we've expanded S2 to take in all of its subordinates. And now we can use integrity to reason that we can get from here, sort of through here, knowing that this component won't have any impact on these components because there's no authority between them. But integrity doesn't tell us anything what goes on inside S2 with sort of these resources that it's reconfiguring. Okay, so we need to do some extra proofs that are specific to this system to reason about the behavior S2, so that when we move to this state, we know that we can construct a well-formed policy for D and G. So yeah, so the policy switches in a dynamic system are quite a bit more dramatic, and we need to do some extra proofs to say that when we exit a trusted component, that we can establish a well-formed policy for its subordinates. Okay, so integrity is still useful because it allows us to focus our attention on the trusted component when it's executing, know that it can't have any impact on other subsystems, but we still have to do some extra reasoning about this trusted component itself. Cool. So that's pretty much all I wanted to say about integrity. We've seen how to define access control policies, to show how they relate to states, what the theorems tell us in that case, and then how to use them to build static and dynamic systems. Cool.
Thank you, Matt. Thanks, Matt. We have some time for questions.
Hi, Chungshun from ESO. And I'd like to know if there's some applications for the dynamic systems integrity proofs. So does it enable, for example, hardware Ethernet sharing, like how it happens in VMware or VirtualBox?
Can you expand a bit on how what actually happens in that system? You're talking about things like VirtIO buffers.
So VMware allows you to configure your Ethernet connection to your VMs through a NAT router or host only, for example. So these are dynamic changes that a vanilla seL4 cannot really do. But if you have the right policy framework for these dynamic systems, does it allow you to show integrity for Ethernet hardware sharing, for example?
I think so. so in the dynamic system, what you end up with is sort of a hierarchy. Yeah, one thing I didn't mention is that you can repeat this reasoning sort of up a hierarchy so that these two supervisors might have their own supervisor. But I think this kind of scenario where you might have some passive resources here for, I don't know, your Ethernet frame buffers. So the supervisor can take control of that subsystem and sort of reconfigure those resources to a new configuration. So I think, I don't know the specifics of what you're describing, but I think it should be possible, but it's probably a significant amount of work.
Thank you.
Yeah.
Hey, Matt.
Hey.
Good job describing a very challenging topic. I wanted to ask, you seem very happy with this situation. And for us, it's very interesting to know, well, if we wanted to build bigger systems, realistic systems, dynamic systems in the future, and then verify them, or verify some properties of them, what would you say you'd want to change about the proofs to make that better, make it more what you want, or just you seem to have a really good understanding of them? What was done that you would have done differently?
So one thing that I think is a little bit lacking is that the integrity, if I just go back to here, the integrity relation, which describes what changes are allowed for a policy, is a little bit too relaxed, I think. Like it tells you that a thread can be modified or an endpoint can be modified, but it doesn't tell you that the way in which it can be modified. The kind of thing I was describing with the dynamic systems is a bit like a separation logic, where the integrity theorem allows you to focus on sort of local concerns when you're proving something about a trusted component, and then lift that, like it's kind of like a frame rule from separation logic, allows you to lift the result of that reasoning to a global property. So I wonder if it might be a little bit better if it was actually an actual separation logic where you could know exactly what change it was going to make on a transition to sort of give you, sort of system level reasoning if you have that sort of hierarchical structure. That's probably what I would change.
Great. I think that's all the time we have for questions now. Let's thank Matt and Raph again for this.